Okay, this is exam 3 for spring 2012, physics 102. Which of the following statements is true? Alright, Newton believed light was a particle because of refraction. He believed light was a particle because of reflection, so that's not true. Young showed light was a particle through the double slit experiment. He showed that light was a wave through that. Einstein showed light was a particle through the photoelectric effect. Alright, that's what he won the Nobel Prize for, remember? That is the correct answer. And this last one is not true. Huygens believed light was a wave because of reflection. He thought that light was a wave because of refraction. So the answer is C. Two mirrors sit at an angle of 120 degrees to one another. A ray of light is incident at 50 degrees on the first mirror. What is the angle? What is this angle? The angle of reflection. Alright, so this angle is 50. That means that this angle right here has to be 40 degrees. And then that means that this angle right here has to be 180 minus 160, which is 20 degrees. 160 because these two angles add up to 160. And in a triangle you have 180 total degrees. So if that angle is 20 degrees, that means that this angle is 70 degrees, which means that the reflected angle is also 70 degrees. So the answer is C for number 2. Which of the following is true? Right, I'm going from a bending away from the normal. If I consider my wave fronts, it's going to have to be traveling faster here in order to go in this direction. That means that N2 must be less than N1. So number 3 is A. Alright, what is the speed of light in glass? Alright, well the speed of light actually slows down. It's related by this way. 3 times 10 to the 8th meters per second over 1.5. So that's going to be 2 times 10 to the 8th. So number 4 is D. A ray of light is in a medium as shown in this figure. What is the angle theta? What is this angle? That the ray of light emerges from the water. Alright, so we can just forget about this completely, and we'll just figure out what is the angle going from here to here, and then the angle going from water to air. Alright, so for air, N is equal to 1. So first let's say 1.4 sine of 30 equals 1.3 sine, and I'll call this theta 3. And then we solve for theta 3. That's going to be we get 33 degrees. That's not the answer, however. That is the ray of light comes here at 33 degrees. But I want to know what is this angle. Alright, so I say N3, that's 1.3 sine of 33 equals 1 sine of theta. I solve for theta. Let me do it over here. And I get 45 degrees. So the answer is D. Theta is equal to 45 degrees. Right, number 6, consider the light ray in an acrylic medium as shown in this figure. What must be the angle theta 1 for the ray to undergo total internal reflection? So I'm looking for the critical angle, and that occurs when theta 2 is equal to 90 degrees. So I just say N1 sine theta 1, that's 1.4 sine of theta 1 equals 1 sine of 90. And then let's see, this is theta 1. And I solve for theta 1. And it's 1 divided by 1.4. And the inverse sine of that, I get 46 degrees. That's C. Your eye consists of a convex lens that creates an image on your retina. You look at a very distant object and your eye has a particular focal length. In order to focus on a nearby object, how much the focal length of your eye change? Alright, so if you're focusing on a far away object, it means that the image is at the focal point, which is going to be at the retina. However, if you're focusing on a nearby object, alright, it means that the image is back here, still at your retina. However, the focal point has to be right there. So the focal length is actually going to decrease. So number 7 is B. Which of these appropriately lists the photons in order of energy from the least to the greatest? Alright, let's see. X-rays is a high energy. Radio, ultraviolet, not that one. Looks like C. Radio is the lowest energy, then infrared, then ultraviolet, then X-rays. So number 8 is C. Which of these rays is drawn incorrectly? That would be B. B is drawn incorrectly because it shouldn't go through the center of curvature. It should go through the focal point when it's parallel to the axis. The other two are correct. Alright, most cameras have an aperture to block the outer edges of the lens. What is the purpose of this aperture? It's to reduce the effects of spherical aberration. So number 10 is A. The person in this figure is standing in front of a flat mirror. There's a star in front of the person as shown. Where does the person see the image of the star? Alright, the image of the star, the object is here, the image is going to be there. It doesn't matter where you stand, the image is always going to be at the same location. Which of these aberrations occur in mirrors? Okay, let's see, geometric and diffraction, those aren't really aberrations at all, just made those up. Chromatic aberrations do not occur in mirrors because they are a result of refraction, and mirrors don't refract, they only reflect. So the answer is A. Number 12 is A. Alright, where is the image formed by the second lens in this figure? Alright, so first let's just find Q1. That is, where is the image formed by the first lens? Q1 is 1 over F1 minus 1 over P1 to the negative 1. That's 1 over 10 minus 1 over 30 to the negative 1. That's 3 over 30 minus 1 over 30, which is 2 over 30, and we inverse that, we get 15 centimeters. So, the first image is right here. 15 centimeters from the first lens. That means that P2 equals 15 centimeters. But look, now the object is at the focal point, so that means that there is no image. So number 13 is D, because the image from the first lens, right here, is the object for the second lens, and that object is at the focal point of the second lens, so there's no image at all. You stand 100 centimeters in front of a mirror, so P is 100 centimeters, and find that your image is 1/2 your actual size. M is equal to 1/2. What is the focal length of the mirror? Alright, so first of all, we want to know, is this upright or inverted, this image? This image is smaller than you, so that has to be a convex mirror. So that means that it's an upright image, and so my magnification is positive. Alright, that means that my Q is going to be negative. I want to find the focal length, but first I have to find my image distance. It's a two-step problem, similar to your homework. My image distance is equal to negative M times P, which is going to be negative 1/2 times 100, which is equal to 50 centimeters. Excuse me, negative 50 centimeters. So Q is equal to negative 50, P is 100, and now I want to find the focal length. Better come out negative because I know that convex mirrors have a negative focal length. F is 1 over P plus 1 over Q, the inverse of that. That's 1 over 100 plus 1 over negative 50. The inverse of that, let's see, that's equal to 1 over 100 minus 2 over 100 is going to be negative 100. Alright, so that is C for 14. You look in a mirror and see an image of your nose that is bigger than your actual nose. Which of these options correctly give the type of mirror and explain the image? Alright, the only mirror that makes a bigger image than the object is the convex mirror, or excuse me, the concave mirror. Alright, so, well, that gives us the answer right away. So it has to be A, because it's not a flat mirror, not a convex, and not a convex there. Also, in order to be bigger, or excuse me, with a concave mirror, when it's bigger, that means that you're holding it really close to your face. Remember the magnifying mirror we had in class? You have to hold it up close to your face. That means that the object is inside the focal point. And if it's inside the focal point, it's going to give you a virtual image. And if it's a virtual image, it has to be upright. So the answer is A. Alright, what can you do to see more of yourself in a flat mirror? The only thing you can do is get a bigger mirror. If you move away from the mirror or towards the mirror, it doesn't affect how much of yourself you see in the mirror. Interference occurs in what type of waves? Interference occurs in all types of waves. Sound, mechanical, or light waves. Remember we saw the water waves, they interfere as well. Next time you're out on a lake, just take a look. You can see the interference patterns sometimes if you look closely. What statement best describes the phase of these two waves? Alright, these two waves are offset by a half wavelength. That means this distance is a half a wavelength. We also call that 180 degrees out of phase. So let's see. Not that, not that. Oh, wait, excuse me. Yes, that, not that, yes, that. So 2 and 4. Two coherent waves have a wavelength of 4 meters. The first wave travels a distance of 3 meters, and the second wave travels a distance of 11 meters. That means that the path length difference is 11 minus 3, which is 8 meters. So one of the waves travels an extra 2 wavelengths, but that's still going to make it be in phase when they rejoin. If it travels extra 2 wavelengths, so that's going to be B. You get constructive interference because the 2 waves are still in phase. This would be like the second order maximum. Alright, I have one wave that travels 2 wavelengths extra, and that gives me my second order maximum, but I still get constructive interference. Diffraction gradient is 540 lines per millimeter. How far apart are the two adjacent slits on the grating? Alright, so I just do 1 over 540. And I get 1.9 times 10 to the minus 3. That's in millimeters though. To convert it to meters, you move that decimal place over 3 places. So the answer is 1.9 times 10 to the minus 6. That's number 20. A laser beam is incident on 2 slits, 0.1 millimeters apart. So just write down what I got. It's a pretty basic problem. 650 times 10 to the minus 9 meters is lambda. D is 0.1 times 10 to the minus 3. How far is the second bright fringe? So M is equal to 2, and L is equal to 5. I first have to find theta. Theta is equal to the inverse sine of M lambda over D. Inverse sine of M lambda over D. Putting in those values, 2 times lambda over D and then inverse sine, I get 0.745 degrees. And now I want to know how far apart they are actually on the screen. So y is equal to L tan theta. You can go back and look at your definition of tangent, opposite over adjacent. That is y over L. You can draw out the triangle as we did in class. And so that's 5 times the tangent of that angle. And I get 6.5 times 10 to the minus 2 meters. Which is 6.5 centimeters. That's A. In the Young's-Dibble slit interference apparatus, by what factor is the distance between adjacent light and dark fringes changed when the separation between slits is doubled? Alright, we want to consider 2 things. D sine theta equals M lambda, and then also that y is equal to L tan theta. Alright, so if I double this by 2, that means that theta is going to go down by a factor of a half. Alright, and if I take theta down by a factor of a half, that means that y is also going to go down by a factor of a half. So for number 22, the answer is B, that the distance between the fringes, or the bright spots, is going to go down by a factor of a half. Alright, something that's sort of inferred here is that the angle theta is small, and then we can make a small angle approximation and that is that theta is equal to the sine of theta, which is equal to the tan of theta. Alright, number 23. After light from a source passes through two slits, a first-order bright spot is seen on the wall at point P. What labeled distance is necessarily equal to the wavelength of the light? So we're looking at the first-order fringe at this point, and I want to know which of these distances, A, B, C, or D, has to equal one wavelength of light. Well, this is our path length difference, B, and so it has to equal one wavelength of light. At what angle will the second order maximum occur for a wavelength 400 nanometers? Using a diffraction grating with 1,000 lines per centimeter. Alright, so M is equal to 2. Lambda is equal to 400 times 10 to the minus 9 meters. And then I want to find D. D is equal to 1 over 10,000. Which is 1 times 10 to the minus 4. But that's in centimeters, so it's 1 times 10 to the minus 6 meters. Now, I want to know the angle, the inverse sine of m lambda over d. Putting in those values, m, lambda, and d, I get this, 2 53 degrees. 53 degrees. So that's C for number 24. Light of 500 nanometers is on a double slit. A width of 1,000 nanometers. What is the highest order presence in the diffraction pattern? Alright, the orders go away when theta is equal to 90 degrees. So I can say that d sine theta equals m lambda. Theta is as its max when theta is maximum at 90 degrees, so that means that this goes to 1 because the sine of 90 is 1. And then I solve for m, d over lambda. D is 1,000 over 500. I'm just going to keep them in nanometers since they're the same units. That means that I get 2 orders, but I can't get more than 2 orders. I get exactly 2 orders and no more.